Good afternoon. Okay. All right. Happy Friday. We're 6 weeks in. Pretty intense. And we're going to start off our last topic of this unit. So we have one more unit after this, just not super long, just talking about limits. For our sequences and series unit, this will be our last lesson. So we'll go over this today and then on Monday. And then that'll be the end of this unit. Again, though, you can already go through and take the PFA sequences and series because this stuff that we're about to learn today and Monday is not on there because I don't know how to turn that into PFA questions, as you'll see. But let's go ahead, kick it off, get through it, get done. You guys can head outside. I'm sure Megan's already there. So, mathematical induction. So what is mathematical induction? Well, let's take a look at an example. Okay, let's look at the partial sums for the series of odd numbers. Okay, 1 is 1. 1 plus 3 is 4. 1 plus 3 plus 5 is 9. 1 plus 3 plus 5 plus 7 is 16. 1 plus 3 plus 5 plus 7 plus 9 is 25. 1 plus 3 plus 5 plus 7 plus 9 plus 11 is 36. Okay, and so on. If we continued this, so this is just adding a term, adding an odd number each time, but hopefully you can see a pattern here, kind of like when we built the sequences, right? We were like had to write the explicit form, figuring out what the patterns were ourselves. So for this series, if I want to know like a formula for the partial sums, well, look at what all these numbers have in common. 1, 4, 9, 16, 25, 36. What property do they all have in common? They're all perfect squares. Okay, so oops, there we go. I lost my mouse. Here we go. It's just n squared, right? If I have one term, 1 squared is 1. If I have 2 terms, 2 squared is 4. If I have 3 terms, 3 squared is 9. 4 terms, 4 squared 16. 5 squared 25. 6 squared 36. All right, so it's pretty cool to see that this pattern exists. Now, the question that I would have though is, how can I be sure that this works for every single number? Right? I can see that it does work for 1 through 6, but how can I be sure this will work for every number no matter what? How can I be sure that this is the bona fide formula? Right? And I'm not talking about just like, oh, plug in 7 and plug in 8. How can I be sure that this works for every single number on into infinity? If I do 3,456,000, how can I be sure, or 57, how can I be sure if I add up all those odd numbers, I'll just get that number squared? Well, I can't check every number. That's ridiculous. So instead, what we're going to use is what's called mathematical induction, where we will be able to prove this will work for every single number. Okay, so we have what's called the principle of mathematical induction. We'll also probably call that PMI because it's kind of a hassle to write principle of mathematical induction. This can be kind of referred to as the domino effect. So here's basically the steps that are happening whenever we do mathematical induction. All right, I'm gonna explain this via dominoes, and then we'll explain it how it applies to math. So if I have a bunch of dominoes standing up, right, my step one, so I'm gonna kind of make this analogous to a process that we're gonna do, is will one domino fall over if I push it? Right? If I just set up one single domino and I push it, will it fall over? Yes. Okay. Yes, it will. Get your own dominoes. You know, go get some from your grandma. All right. My grandma has a ton. Okay. My step two then is thinking, well, if any domino in a line falls, will the next one fall? Okay, so now this is just talking about any domino. If I have a line of dominoes and I pick out any single one of them, if I knock over that one, is the one that's after it going to fall down? Assuming that this is, you know, a line of dominoes where they're all next to each other and whatnot. Yeah, it will. Okay, that's how it works. If one domino falls over, the next one will fall over. You can test that if you want. All right. So then step three, we can conclude that if the first one falls, then all will fall. Right? Because we showed with just one, our first step was just show that one domino will fall over if I push on it. Okay, great. It works for this one domino. And then I've shown, step two was, do we know that if a domino falls, the next one after it will fall too? Yeah, we know that. So what can we conclude then? We can conclude if I knock over that first domino, well, step two proved that this next one will fall. And if this one falls, then that we know that if a domino falls, then the next one falls. Great, so that one falls too. And we know that if this domino falls, the next one falls, so the next one, and the next one, and the next one, and the next one. Okay, and onward and onward and onward. That no matter how many dominoes there are, we can conclude that every single domino will fall. Right? That's the idea of what we're doing here. I don't know, that may seem confusing, but I do think it is useful to think about it like this. Okay, so kind of more interpreted in math. So I'm gonna go through three phases of this explanation. So first phase is dominoes. Phase two is kind of in words. So what I'm talking about for math is we're gonna prove something is true at its most basic case. So that's like the first domino, right? Just one domino being there, boop, pop it over, it's gone. Second step, prove that if any case is true, then the next one must be true as well. Okay, so can we prove that if any domino falls, right? It doesn't matter which one, but if any domino falls, can we prove that the next one will also fall? And then step three, conclude that every case will be true. So that's what we did. We knew that if the first one falls, then every subsequent one will fall as well. All right, so now here's the nitty-gritty math steps. All right. Step one, first we're going to plug in 1 for n. So like I said back here, the most basic case. So for us, the most basic case will be if I plug in 1, right? Because that's the smallest natural number. So if I plug in 1, is this thing true? Okay, great. Step two, we'll assume that the kth term is true. Right? So again, like since we know that dominoes can fall. So can we show that the k plus 1, so k plus 1 would represent like the next domino. So can we show that the next one will fall? If we already know this one's falling, can we show that the next one will too? You'll need to replace all k with k plus 1. Work until each side are identical. Okay, this will involve a lot of simplifying and manipulation. Okay, so we might need to distribute, factor, rearrange things. Who knows? It's quite warm. I agree. Seems to be. I don't know. I only went outside for a little bit earlier, but I'm about to head out after I'm done with all this school stuff. Finally, state your conclusion. So we will start off by writing by the principle of mathematical induction, or we'll write by PMI. It's like 80. That's awesome. I can't wait. I'm excited. So let's do 2 examples. Well, there's 4 total. We'll do 2 today, 2 Monday. Prove by mathematical induction that, so this is the thing that we talked about earlier. Can we prove that for every series partial sum of odd numbers, it'll just add up to n squared for all natural numbers? Remember, natural numbers are like 1, 2, 3, 4, 5, 6, 7, 8, etc. Okay. So, step 1. Okay, step 1 is where we have to show, is it true for n equals 1? So that means we're just going to plug in 1. Right? So 2 times 1 minus 1. And then the other side should be 1 squared. 2 times 1 is 2. 2 minus 1 is 1. 1 squared is 1. Okay. So yes. We have shown that it is true at its most basic case. All right? And for us doing these problems, the most basic case is always plug in 1. Is the formula true? Yes. All right. But if we had gotten like 3 equals 1, well, then our formula is already busted. It doesn't even work for the most basic case. Okay. Step 2. So look at step 2. Assume that the kth term is true. All right. So we got to do some writing on these problems. So we assume it is true for n equals k. All right, so that means I'm just going to go through my equation. Instead of n, I'm going to plug in k. So plus 2k minus 1 equals k squared. Right? So step 1 was just showing, will the first domino fall? Yeah, 1 equals 1. We've shown that that most basic first single domino will fall. Okay, step 2, we're showing... What a way to get a hold of me. Hi, Janasia. Accept what, PFA? You didn't even request anything, you dork. Did you request something? Psych? I'm not your psych teacher. I can't approve those. That has to come from Mata. I can only do math. That's all I'm allowed to open. I know, right? Yeah, you're gonna have to talk to him. Sorry, dude. Oh, what if I could? Dr. Stanley will hunt me down. Hashtag this sucks. I agree. Sorry. Okay, so we're assuming it's true for some n equals k. So this is like where we said, well, let's just pick any domino in the line. Doesn't matter if it's the second domino or the 450th domino or whatever. So we'll say we know that this single domino, wherever we picked it out, will fall down. Right, and we just plugged in k because k represents whatever spot that domino is in. It doesn't matter. So step 3, we need to prove it is true for n equals k plus 1. Right? And so remember, k plus 1 represents the next term or the next domino. Can we prove that if any domino will fall, that the next one will then also fall down? All right, well, let's try it. So what we're going to do is we're going to take our formula here, and now I'm going to plug in, here we plugged in k, now I'm going to plug in k plus 1. So 1 plus 3 plus 5 plus 7. All the way up to 2. But instead of n, I'm plugging in k plus 1. And then instead of n squared, I have k plus 1 squared. Okay, so our goal right now is to show that these two sides are equal. So right now there's an equal sign between them, but that's just, I mean, we're just plugging in stuff. How do we know for sure? So this is what I said. We need to do some multiplication, some distributing, some rearranging, manipulating, so we can prove definitively that these are the same thing. All right, so k plus 1 is what we plugged in here and here. So we just plug that into our original equation. Okay. So let me actually do some thinking here. So plus 5 plus 7 plus, what's the term that will come before this one? Before the k plus 1 term is just the k term, right? So that would just be 2k minus 1. And then this stuff would be the next term after that, right? 2k plus 1 minus 1. Right, so all I did was just consider what term would be coming, because I know there's a bunch of terms in here in this dot dot dot. So I'm just asking, how would I represent the term that comes before this one? Well, instead of k plus 1, it would just be k. Right, now take a look at what I have here. Right? That's the same thing as what I have right here. And I already know that this stuff, from step 2, I already assumed that it's true that this stuff is equal to k squared. So actually, all this stuff that I just circled is k squared. Right, so I used my information from step 2 to say, hey, wait a minute, all of this stuff, I could just write that as k squared. Okay, so now let me keep rearranging. So that's k squared plus distribute 2k plus 2 minus 1. 2 minus 1, so that's k squared plus 2k plus 1 on the left side. And on the right side, k plus 1 squared, well, if I distribute that out, I would get k squared plus k, so plus 2k plus 1. And check it out. The left side and the right side are equal. That was exactly my goal. That was what I was trying to prove. All right, I did it. I'm a master. Okay, so once I've proved that those are actually equal, then I can conclude. So you're going to see me draw this thing. This is like saying therefore. It's commonly used in math proofs like this. So we'll say by the principle of mathematical induction, or PMI, because I'm too lazy to write that out, then our equation, 1 plus 3 plus 5 plus 7 plus all the way up to 2n minus 1, whatever it is equal to n squared. And we have proved that for all natural numbers n. Okay, so again, the little dots in the triangle represents therefore. So we need this final statement. So there's a lot of specific things we have to write in these problems. We have to write, about our, assuming it's true for n equals 1. We have to write, we assume it's true for n equals k. We have to write that we want to prove it to be true for n equals k plus 1. And then we have to finally make a conclusion. Right? It's like writing a freaking essay out here. If you are super fancy, now this is if, for all natural numbers n, if you want, is this just the basics for calc proofs? No. No, this isn't specifically related to, like specifically related to calculus. This is just a high-level math concept that's used in pretty much any field. But we'll use some of these ideas in calculus. So if you're super fancy, instead of writing for all natural numbers n, what you could also do is you could write this. All right, there's upside down a, n, this little kind of almost like an E looking thing, but really it's just like it's like a C with a line through the middle, and then an N with an extra bar. So the upside down A represents for all. The capital N with the bar represents the natural numbers, and the little n represents the little n. So you can write whatever you want. I don't care. You can just write it out in words. But if you really like symbols and such, you can write it this fancy way. Okay, so let's try one more for today, and then we'll do a couple more Monday. So prove by mathematical induction that 4 plus 8 plus 12 plus 16 plus all the way up to 4n is equal to 2n times n plus 1 for all natural numbers. So on the left here, what this is saying is if you add up all of the multiples of 4, right? 4 times 1, 4 times 2, 4 times 3 times 4 times 5 times 6 into never. It would just equal this right here, 2n times n plus 1. Maybe. Let's prove it. All right. Step 1. So, is it true for n equals 1? So let's just plug in 1. 4 times 1 equals 2 times 1 times 1 plus 1. Wow. So yes, This is true for the most basic case. Right, the most basic case. We are step one is proving if I set up a single domino, that first domino, if I push it, will it fall over? Yes, it will. Great. Okay. Step two, so we got to do a little bit of writing. So we assume it is true for n equals k. So I'm going to use this exact same thing, except I'm going to plug in k. And so k represents just any spot, any number, doesn't matter. Any domino in the line, if we pick out any one of those. So 4 plus 8 plus 12 plus 16 plus 4k instead of 4n. 2k times k plus 1. Right? Yes. So we're assuming this is true. Right? So when I pick out any domino in the line, I'm assuming it's true that if I push over that domino, right? So now I'm going to see, does that mean the next one will fall? Okay, so step 3. Show it is true for n equals k plus 1, or show or prove, whatever. Prove it is true for n equals k plus 1. Okay, so not only is this going to go up to just 4k, but then it'll go up into the next term after that, which is 4 times k plus 1. And I'm trying to show that that would equal 2, but instead of k, I'm doing k plus 1, the next term, times k plus 1 plus 1. Okay, so basically I just took this equation, but anywhere there was originally, I shouldn't use green. Anywhere there was originally just a k, I replaced that with k plus 1. And again, my goal, just like on the last one, show that both sides are equal. So just because there's an equal sign between them, I can't really see that they are definitely equal. So can I manipulate it until, like on the last one, we got exactly the same thing. K squared plus 2k plus 1. K squared plus 2k plus 1. All right, that's my goal. So what this will do is prove that if any domino we push it down, the next one will also fall down. All right, so again, take a look at what I have here. This is the same thing as this, right? This is the same thing that we already proved from, or we already assumed to be true from step 2. So what that means is we already know that's equal to 2k times k plus 1. And now we'll just add in the rest of our stuff. So this term plus 4 times k plus 1. And then equals 2 times k plus 1. And then k plus 1 plus 1, I'll write as k plus 2. All right, so let's do some rearranging and hope that we get the same thing. So I'll distribute for all of this. 2k times k, 2k squared. 2k times 1, 2k. 4 times k, 4k. 4 times 1, 4. 2, I'll FOIL these out. K plus 1 times k plus 2. That would be k squared plus 3k plus 2. On the left, combine like terms, so 2k squared plus 6k plus 4. On the right, distribute the 2. 2k squared plus 6k plus 4. Look at that. We have the exact same thing on both sides. So, step 1 is true. The most basic case is true. Right? The first domino we know will fall over. Step 2 and 3, we know that if we pick any domino, doesn't matter where, whether it's the first one or the 3,000th one, we know if we push over that domino, the next one's going to fall. So adding that all together, we know push over the first domino, it's going to make the next one fall, which will then make the next one fall, and the next one fall, and the next one fall. So it'll prove that all the dominoes will fall. So, or for us, in our case, what this proves. So let me do all my fancy stuff. So my little triangle, which means therefore. So therefore, by the principle of mathematic induction, our equation that we were trying to prove, 4 plus 8, oops, not 4 plus 12, 4 plus 8, all the way up to 4k, or actually I should use n since the original. We use n in the problem to work with stuff, but, or sorry, we use k in the problem to work with stuff, but n for the actual formula itself, equals 2 times n plus 1, right? That was what we were trying to prove from the beginning. So this is true. What? For all natural numbers n. And again, if you want to be super fancy, you could write this instead of that stuff that's underlined in red, but I do not care whatsoever. I just like it. I like using that. So, and that's not just some weird thing that I came up with. That is these are legitimate mathematical symbols. Okay. Questions? Comments? Anything for me? Again, we'll do these next two. So these first two were all about like adding up terms of a series, but these next two, like proving something is divisible by 4, or proving it's divisible by 3. Okay, so it'll be slightly different, but we'll use the same overall steps. Step 1, first domino will fall down. Step 2 and 3, if we pick any domino, will the next one fall? And then finally conclude, we know all the dominoes are going to fall. What if it isn't true? Then when we get to our step 2, or like when we get to step 3, as we're trying to get these things to equal each other, it won't work. The left side will just, maybe I have 2k squared plus 6k plus 5, but then on this side I have plus 4. Then we don't have anything special. Then we would just state it's not true for all natural numbers n. That's all we would say. Or even if we went for our very first step and plugged in 1 and it wasn't true, well, same. Well, okay, great. It's not true then for all natural numbers. I don't think we'll have any of those, though. I think everything that we have is a true statement. We're just practicing proving that it is true for sure. It's a good question. All right. Well, that's that. We'll finish that up Monday. Until then, I sent out a homework sheet with today's assignment. So you could practice those. You probably couldn't finish it until we do Mondays. I mean, maybe you could. But there's a couple little tricks that I have to teach you about the next 2. But the ones that are just like adding things together and getting a certain formula like this, you could definitely do that. But practice those and take PFAs, take sequences and series for sure. Take anything else you need to take. And I'll see you on Monday. I hope you have a great weekend. Get outside, go into the sun, get that vitamin D. Makes you feel better. Right? And that's that.